Hi everyone, today I'm going to go over the memory reading and basic assembly worksheet for the Lab 5 activity. To start, let's look at our memory table. Over in the gray rows, we have our memory addresses, and below that, we have our values. The way that we'll read our memory is starting at 0, 0, we'll go from right to left, and then at 0, 7, we'll jump all the way to the right to 0, 8, all the way to the left until we reach 0F, and then after that we'll go down to the next row, and then we'll read from right to left, go all the way to the end, and then right to left. We should also keep track of which registers we'll be using for today's problem. I can see that we'll be using RAX, RDX. Remember that EDX refers to the last 32 bits of RDX. And I also see EBX, so the full register name will be RDX. So in total, we have 3 registers that we're working with: RAX, RDX, and RBX. Alright, I just drew out the registers for us. Let's review them really quickly. We have RAX, RDX, and RBX. Each of these registers are 64 bits or 8 bytes. And then I also saw that we were working with EDX and then EBX in our instructions. So I made sure to specify that EDX is the last 4 bytes of RDX, and then EBX is the last 4 bytes of RBX. Our first instruction is move 0 into RAX. Our destination register will always be on the right, and then our value over here is 0. In RAX, our value will be 0x, and then since we have 8 bytes in RAX, I'll pad with 7 bytes in the front, and then our 8th byte will be 0. In our second instruction, we will have the same exact value being placed in RDX. In our third instruction, we see a special instruction where we are moving 4 RAX into EDX. Let's break down what this 4 RAX means. This parentheses means we are dereferencing. It means the value in RAX is a memory address. And this 4 in front means that we need to calculate to get the final memory address. Once we have the memory address, we have to use that memory address to find the final value to move into EDX. Again, EDX is last 4 bytes of RDX. How do we go about calculating the new memory address? Well, we have to use indirect memory addressing. We use this formula D, RB, RIS. With these values, we can then add D plus RB plus RI times S. In this particular case, we have 4 is our D, and then RAX, which if we look back is 0. We know that 4 is our D, and then this is our base register. So given this equation, we have to add 4 plus 0x0, which becomes 0x4. Now we have our memory address. Our next step is to use that memory address to find the value to move into EDX. We have our table up here. We can find 0x04, our memory address over here, and then to find the size of the value that we need to move into EDX, we can just look at the size of EDX. As I said before, EDX is 4 bytes, so we're going to start at 0x04 and then count 4 bytes. 1, 2, 3, 4. So we know we'll be grabbing these values. However, our final answer will not be 3236313A, but rather 3A313632. The reason for this is because we're in Little Endian, which means the least significant byte is at the lowest address. So our least significant byte would be 32, because 32 is at the lowest address 4. So we will be moving 3A313632 into RDX. Let's move on to the next instruction. Again, we see these parentheses, so we know that we will be accessing some memory address. And on the right side, we're going to move a value into EBX. When we see that E, we know that we are referring to the last 4 bytes of the register RBX. So let's do some dereferencing. We know that REX is at 0x0, so there's no displacement or any other values that we need to take care of, so we can just go directly to 0x0 and grab 4 bytes. We found 0x0 here, and the 4 bytes are 43, 53, 20, 20. So our final value that we're grabbing will be 20, 20, 53, 43. Let's go into the next instruction. This next instruction has a special value here, ZQ. This Q means quad word, which means we're moving 8 bytes. Over here, since we're moving EBX, which is only 4 bytes long, into RAX, we need to account for those first 4 bytes that we don't know the value of. So we'll just zero those out with our move ZQ. So if we have 20, 20, 53, 43 in EBX, and we're moving that into RAX, we will update the last 4 bytes of RAX to 20, 20, 53, 43, and then the first 4 bytes will be zeroed out. They're already zeroed out, so this is our final answer for RAX. The next instruction is a shift left by 0x20 in RDX. If we're shifting left by 0x20, our first step is to convert this hexadecimal number into decimal. One easy way to do that is use the places method, where you know that this number is in the ones place and this number is in the zero place. So what you do is you multiply the digit itself, so 2 times 16 to the place, which is 1, plus 0 times 16 to the 0, and the final answer will be 32. So 32 bits, which is equivalent to 4 bytes, because you're dividing this by 8 bits per byte. If we shift our RDX left by 4 bytes, then that means we'll remove 1 byte from the left, 2 bytes, 3 bytes, 4 bytes, and then we'll fill in the remaining bytes on the right with 0. So now this is what our EDX looks like. In our final instruction, we will perform an OR operation with RDX and RAX, with RAX as our final destination. Okay, if we OR RDX and RAX, if we OR any number in 0, the final result will be that number. So for this, the first 4 bytes, by ORing 3A, 31, 36, 32, and 0, we get 3A, 31, 36, and 32. And then the same goes for the last 4 bytes of RAX. Since we're ORing that with 0, then our final value will just be 20, 20, 53, 43. And then this will be our final value for RAX. So now RAX will be... So these will be the final values for each of our registers. We have the result of the OR operation for RAX, the result of the shift left, and then RBX. Those first 4 bytes are unknown values, but we do know the value of EBX. Alright, let's go through problem 2 of the worksheet. Our first step is to identify what registers we'll be working with in this problem. I notice we're using RBX, RCX, and RDX. Our first instruction is to move the value of 1 into RBX. Since RBX is 8 bytes, we'll make sure to pad with zeros for the remaining bytes. Our next instruction asks us to calculate the address and find the value starting at that address. And then finally move value into RCX, which is 8 bytes. So let's get to calculating the address. We know that we have RBX and 8. If we compare this to our indirect memory addressing formula, we see that we have D RB plus RI times, if we look at our current if we look at this current instruction, we see that we have RBX is RI times 8, which is, if our RBX is equal to 1, then we have 0x1 times 8, which is 0x8. And we need to grab 8 bytes starting at 0x8 because our destination register is 8 bytes. In our memory table, we have 0x8 over here, and we can grab 8 bytes starting at 46, then 1, 2, 3, 4, 5, 6, 7, 8. So the final value we get is 45. So that's the final value we get, and then we'll place that into RCX. Great. Then our next instruction will also require some memory calculation. In this case, we have 0x18 RBX 4, and we're moving this into RDX, which is 8 bytes. Looking at our formula, we know that 0x18 is D. We don't have a base register, but we do have our index register, which would be RBX, and then we have a scalar, which is 4. So if RBX is 1, then we have 0x18 plus 0x1 times 4, which is equal to 0x18 plus 0x4. This is not equal to 0x22. Instead, what you have to do is do hexadecimal addition. So we have 0x18 plus 0x4. 8 plus 4 is 12, so 12 in hexadecimal is C. Then we have 1 plus 0, which is 1. So our final answer is 0x1C. So this is our memory address. And we have to grab 8 bytes starting at 1C. In our memory table, we have 1C over here, and let's grab 8 bytes. 1, 2, 3, 4, then we go down to the left, 1, 5, 6, 7, 8. So our final value that's going into RDX will be, and that will be the final value going into RDX. Let's move on to our final instruction. Our final instruction asks us to shift EDX left by 8 bytes, 8 bits. EDX refers to the last 4 bytes of RDX. Let's shift this left by 8 bits. Remember that 8 bits is equivalent to 1 byte. We know that in hexadecimal, 1 hexadecimal digit is equal to 4 bits. So if we go 1, starting from the left, and then 2, this is already equivalent to 8 bits or 1 byte. Then we have to fill in the remaining digits on the right with 0. So after shifting left, we would get 0x4E554600. So then we will update EDX to be 4E, and these will be our final register values for problem 2. Thank you for watching, and I hope this video was helpful.